Okay. So topic for today is VC dimension. So before we computed sample complexity in some special cases, like for threshold functions and the seminar for intervals, union of intervals, one can do similar arguments for rectangle aligned axes, boxes. But in general, this method is not really applicable. However, there exists some combinatorial notion which is called the VC dimension, and I will explain it in what it is in the second half of the lecture. It's some purely combinatorial, and usually it is easy to calculate or estimate for specific classes. For example, for decision trees, for especially in theoretical computer science, for circuits and so on, it's easy to compute. For half spaces is another famous example, actually a very important example. And this VC dimension characterizes sample complexity up to a constant. So here, this is a recent result from Haneke, who proved that unless H is trivial in some sense, okay, in the paper it's like I simplify the condition here a little bit. Okay, and I inserted specific constants so that the statement is a bit nicer. And so, unfortunately, the difference between the two constants is quite big, and tighter bounds are not known. So it would be nice to have a bound that's tight within a linear factor, but it's not clear. Maybe for certain classes with the same VC dimension, there are different bounds. Okay, but our goal of the class of this lecture, by the way, the lower bound is easy to prove, so I will probably add it for homework exercise. The upper bound is difficult to prove here, but a long time ago people proved an easier upper bound. So this is a bit weaker because together with the VC dimension there is an extra factor log 4 over epsilon. And this result has another amazing consequence. So the result states that a class is learnable on average if and only if the VC dimension is finite. So if VC dimension is infinite for some classes, like the ones that are, so we saw some examples for learnable classes that are not qualitatively learnable. For example, the set of all classifiers on an infinite set. It has infinite sample complexity for all positive epsilon and delta. It also has infinite VC dimension. Okay, so with this mysterious definition, I let you wait a little bit, and we will first speak about growth functions. Okay. So yeah, both VC dimensions and growth functions, they somehow quantify how rich is a hypothesis class. And so they will later be important to obtain risk bounds. Okay, so, but let me say the two big steps in the proof of this result of Bloomer and Bloomer, Hausler, Bloomer, Ehrenfurth, sorry, this is an E, Ehrenfurth, Hausler, and Warmuth. So it goes into two steps, and I've written them here. So let me remove Haneke's result. Next one space. So the first one, step one, will use growth function. And so I made, so we will soon define growth function. And the first step is to prove an exponential bound times this magical growth function. So that means that probability that the learned class, okay, by the way, this result by the Bloomer et al. It works for any proper consistent learner. So recall what is proper consistent learner. It's a learner that outputs a hypothesis class from H and that is consistent with the training data. And Hanneke's result, the learner for the upper bound, the learner is not such a learner. It's neither proper nor consistent. Well, at least not proper. I forgot about consistent. Okay, so proof will go into two steps, which the first step again holds for every proper consistent learner. And it says that if the size of the training set, so N is the size of the training set, so the probability of outputting a bad classifier, so FSH differs from H, so this measure is more than epsilon. So remember what means this? It just like some shorthand notation, it denotes the risk of the learned classifier. So it is just the measure of the set of all X where the prediction is wrong. Okay, and so this first statement says that the probability that a proper consistent learner outputs a bad hypothesis class with high risk is bounded by something that goes down exponentially in N times the growth function. And the second says that the growth function is bounded by a polynomial, provided that VC dimension is finite. So here we have polynomial times something exponentially small. And that means that if N is just a bit more than epsilon, then this exponential factor will win over the polynomial factor. So after we've proven 1 and 2, it becomes kind of easy to prove this result. The only thing we have to do is choose this value for N. First substitute the bound for G here, then set N equal to this value, and then we get an expression that only depends on epsilon and delta. And then we will work it out. Then one needs to work this out. But note N appears twice. So this big expression appears twice. It's a lot of calculation work, but it's kind of simple. And then you work it out and you will find, so a long calculation, and you will find something that's bounded by delta. And then the proof is finished. Because what you've proven is that for this value of N, we have that this probability is bounded by delta.
Excuse me, can you hear me?
Okay, let me write just for those who might have forgotten what means sample complexity. It is the minimal value of N such that there exists a learning algorithm for which probability that P as H is not equal to H. So probably there exists a learning algorithm for all measures P for all H in the true classifier. The probability that this is strictly bigger than epsilon is at most delta. So that is definition of sample complex. So after substituting, so this value N will be this value, and then we need to verify this inequality, which follows by okay. So this yes.
Yeah, I wanted to ask about the upper bound in the theorem. So the factors are logarithm 4 over epsilon plus logarithm 4 over delta.
Yeah.
Okay, thanks.
Yeah, so be careful. In computer science, log denotes binary logarithm, but in statistical learning theory and statistics, it means natural logarithm. But I will use computer science convention and use ln for natural logarithm and log for binary logarithm. So
Okay.
here we need binary. Okay, but that's just a matter of proportionality constants. It's not so important. Just in case somebody wants to do this calculation, you need to be careful with this. And the reason I need binary logarithm is because here we have 2 to the power minus epsilon n over 2. Okay, so the only thing we will do this lecture is define the sample growth function VC dimension and prove 1 and 2. Okay, so so what means growth function? So let me write down the definition. So growth function expresses, let's define first the growth function for sets. And I denote it by G tilde, and it is the number of dichotomies that appear on the set. And dichotomy is just the set of values that we can have for each. So let me just write it down. So fx1 till xn is equal to size of set of dichotomies. So, and similar for the set. So we just view a set as a list by just taking any order, and then we can define G tilde of a set. So let us look a little example. Let us look at, so for example, G tilde, need some index to indicate the set of classifiers. So for example, G tilde is a threshold function. So if x equals r and t is equal to prime of x minus t, t and r. Okay, so what is the growth function for threshold functions? Gt of n, it is equal to n plus 1. So how do we get this? Okay, and so, as usual, we said we assume that y has 2 elements. So for threshold function, let's for example think about n equal to 3. So what are possible sequences of values that we can have for 3 points? Let's assume we have the points ordered. So what are the values for threshold? We have, for example, all equal to -1. If the threshold is more than the 3 points, then we have -1, -1, +1, -1, +1, +1, +1, +1, and +1. These are the values for the sequence. So these are possible values when we apply functions, threshold functions to 3 different values. So here we see if n equals 3, we can create 4 different sequences of values. Okay, so this is growth function. And let us list a few obvious properties. So for example, growth function is monotone in the hypothesis class. And the growth function is also monotone for set inclusion. So if S prime is a subset of S and H prime is a subset of H, then we know that growth function of H prime, S prime must be bounded by growth function H of S.
May I ask a question?
Yes.
In the definition of growth function, the set f of x1 and so on, f xn, is it ordered or not?
No, it can be any order. So here I just took an example where they ordered for convenience.
Okay, so if we have like list 2 lists which differs only by order, so it is counts as 1 element.
So no. So here we fix the list, I think probably you understand everything, but here we fix the list and the order. And so here, if we flip the order here, it counts as a different element in this set.
Oh, okay, I see. Thanks.
Yeah, I mean the order of the labels, but the thing is that here we fix the order of the input. So here, so we define order of a set. So by transforming first the set to a list, and this you can do in any way you want. But then for this fixed list, we apply this definition.
Okay.
Good, yeah, good point. Yeah.
So that is the growth value of growth function depends on the order we choose on set, or it is?
No, it doesn't depend. Like if you permute all these vectors in the same way, the number of vectors doesn't change.
Oh, okay, okay.
Yes, other property. If we take the union of two sets, 0, 1, H, 0, 2 of n, then we can bound it by, sorry, not n, but a set S, H0 of S plus G, H1 of S. So this is other property, it's clear, right? And size of a growth function is always at least 1 and 2 to the power size of S. So do you know why it's at most 2 to the power size of S?
Because like 2 to the power of S is cardinality of all possible subsets.
Yeah, 2 to the power S is equal to cardinality of Y to the power set of possible functions from S to Y, since Y has 2 elements. Okay. And then we have that growth. Okay, so this is growth function for sets. Now let us add 1 to the definition. Growth function for numbers, g of n of h, and this is equal to the maximum of the set growth function provided, so over all sets of size at most n. So here is the definition. So we have that without the tilde. We have n here. We have that g each of n is equal to 1 if and only if size of h is equal to 1. It's another property. And so all these properties also hold for the growth functions on numbers. Okay, so what else should I say? I think that's it. And so let us now try to prove first step. Let us try to prove 1. And the idea is easy. So idea is that suppose that we output a bad function and then we check the value on the training set. So we generate random training set. Then we will make, with high probability, we will make many mistakes on the training set. Okay, and in this process, we first generate the training set, then we generate test set, and we make many mistakes on the tests. So we generate two sets of size n. So let us generate test set of size n here. Hello, yeah, it's okay. So let us generate test set of size n. And then we see there are many mistakes. What can we do if equivalently? So know that we generate two sets of size n. We can generate both sets, and let us put them in a list of length 2n, the first set here, the second set here, and then let us scramble them. And afterwards, we again get two sets which are randomly scrambled. So now we didn't change. So now we have a new training set and a new test set. And we didn't change anything on the okay, sorry. Okay, forget about this explanation. I was a bit distracted. First, let us review what we did last time. So we gave a bound on the sample complexity. So I didn't explain why we need all this, which is a pretty important thing. I should have explained first. So last time we proved that the sample complexity of H, epsilon, and delta for finite delta is bounded by 1 over epsilon ln size of H over delta, right? And this is nice. We also got, but this is useful for finite H. We also considered some infinite H, for example, threshold functions. And there we said that sample complexity of H epsilon delta, so for threshold functions here, is bounded by 1 over epsilon ln 1 over delta. And yes, and as I started to explain, some people say we can transform in a computer. Every classifier has a finite representation. We can view it as a bit string because eventually in our computer it's described by a bit string. And so we can just use the size of the bit string to represent classifier and get a bound on the sample complexity for it. It's a trick that always worked, but it's very strange because if somebody decides to compute classifiers with higher precision, then the sample complexity goes up. And in practice, and then this bound is even worse than theoretical bounds. So we want to have a nice theory that exploits like geometric properties of classifiers or combinatorial properties. So that's why we care about it. But know that this is proven using a union bound, and we need to get rid of the union bound. And the plan to get rid of this problem is to transform it from a problem on an infinite set of classifiers to a finite set of classifiers. And we will do it by generating test set and then randomly scramble training set and test set. And then we will study this random permutation of training sets and test set. So this is the whole idea. And then we forget where this training and test set comes from. So it's incredibly important result that we will prove here. And another striking thing that will happen with growth functions. So the main tool is growth functions, and the main powerful observation is this inequality. So if this is,
I'm sorry, can I open the door? So the was can go.
Okay, yeah.
But I am a bit scared.
Yeah. Okay, there is some animal flying around here. Yeah. Okay. Yes, and so here's something incredible happens. So either growth function is bounded by a polynomial, or growth function equals 2 to the power n for all n. So there are the only two behaviors, and we will soon see why this happens. Okay, but now let us go to the proof of 1 and 2, and then we get the theorem. Okay, so proof of 1. as I already started to explain, the plan is to generate a test set of size n and view that the classifier is bad. Then with high probability, we have many bad elements in the test set. Then we will scramble training set and test set. And we know that proper consistent learner only outputs classifiers that are consistent on the training set, make zero error on the training set. So that basically, in order to output a classifier after scrambling all the for a given candidate classifier in H, all the mistakes need to be in the test set and zero on the training set. Otherwise, algorithm will not output this. And this is exponentially small probability. And that's how we get this exponent here. But we still need to apply some union bound. That's why we get this. Okay, but let me go into details now. Yes. So, so the first lemma says that if test set is probability so the probability of H bigger than epsilon is smaller than 2 times probability that so here is the W. I will use the notation WG is equal to the set of inputs where G makes a mistake. So 2 times probability of WG intersect T. So here we will generate T. And we will have both S and T are generated by Pn. The size of Wt is equal to epsilon n over 2. This is the first step in mathematics explained. And so number of mistakes that FSH will make on T is with so probability that we generate classifier is bounded by 2 times probability that we make at least epsilon n over 2 mistakes on the training set that's generated independently from the on the test set that's generated independently from the training set. So this is the lemma. Okay, let us prove this lemma. And so for this, we will consider just a simple observation. Imagine that we do some experiment. In an experiment, some event E appears. So if E appears with probability B, then, or let's say epsilon, then in n repetitions, E happens, or event E happens at least and epsilon over 2 times with probability at least 1/2. No. Basic observation. Why is this true? Well, you can look to binomial distribution and you see it's increasing below the mean. So binomial distribution is increasing below the mean. So that means that the first half, cumulative probability of first half, must be at least half of probability of cumulative probability of the rest. So this is kind of obvious thing. And now we get this lemma just by using that probability A of an event A times probability of an event B given A is bounded by probability of B. Okay, so what is probability of, so what is B? B is this event that we want, and A is this event here. This is event A.
Could you please remind what's the difference between S in the lemma and the SH?
SH is the training set plus the labels. So the learner, so S is the list x1 till xn, and SH is the list of pairs x1, h of x1.
And it is fixed set.
No. So if we fix through, so S is a list of inputs, and SH is list of input-output pair.
Okay. I
So
see.
supervisor gives labels to the learner algorithm.
Mhm.
And so here we generate S randomly, and here we generate S the training set S randomly and a test set randomly. So in these probabilities, they go both over S and T, but here we don't use the set T. And so here, but it doesn't matter for this rule. And this is just some Bayes rule. Like this is equal to probability of A and B, and then we drop A, so probability can only increase. Okay, and so now these two things imply this lemma. Right, so we say this is A, this is B, and we know that conditional probability is at least 1/2. So this conditional probability is something that's 1/2 or more. So if we divide it out, we get here a factor 1/2 or less. So if we replace it by 1/2, it can only be more. No. Sorry, here we have yeah, sorry, conditional probability is at most 1/2. So sorry, B is probability that, yeah, the negation of this event. So we say with probability at least 1/2, we see it many times. Oh, wait. Sorry, to prove it, we need this with 1/2 here. So we bring 2 to here, we get 1/2. Yes, and we know that here stands 1/2 or something more. So yeah, nothing happens here. Okay, and so lemma is proven. So now we go to second step. Second step will be that so let me remind what is second step. So in the second step, we will say that probability, and we generate U according to, so we generate a list of length 2n, then probability that the learned classifier makes few mistakes is small. So that means that WFSH intersect U is bigger than some value K, will be smaller than the growth function of 2n times 2 to the power minus K. This is the second lemma that we will prove. Okay, so to see that together they imply our first step, that they imply 1. So we just set K equal to the floor epsilon n over 2. And we note that WFSH never makes a mistake on S. So this intersection is equal to this intersection because we have a proper learner. So there are no mistakes on S. And so we set U equal to S plus T. So concatenations of list S and T. And we realize that this intersection equal this intersection. So again, W are the set of places where this function makes a mistake, but on S it makes no mistakes.
Once again, so we have random set U, and we set our training set to like the first half of U.
Yeah.
Okay.
So after we prove this lemma, we are finished with one. So let's now prove lemma. Okay, and proof is very short. So let us fix G in our class. And let us assume that WG intersect. So there are at least K mistakes on the set U. Now let us apply the technique I already explained. So let us generate U with this condition and then randomly scramble U. So then probability that that WG intersect S is equal to 0. It is bounded by 2 to the power minus K. So S, I define S as first part of U. So S is equal to U1 till UN. And so what do we here? Let us fix U. But then randomly permute S and T and 2. Okay. Sorry, I didn't explain clearly. So this we already explained. So I need to explain this, and here lemma S is random, it is first half of U. First half of U. Okay, so oh, sorry, I should. Sorry, I didn't write the lemma right. Sorry. Okay, so fix U of size 2n. And then probability over random half. So we will then pick a random half of U, call it S, and give it to the learning algorithm.
So S either first part or second part of U.
First part. Yeah, okay, it doesn't matter. Let's say it's random first half of U. It is random half of U. So you just take randomly half of the items in the list. There can be repeated elements in the list, but it doesn't matter. So you just pick half of the indices and then collect them to be S.
So like the probability space is like picking n random indexes from from 1 to n.
Yeah.
Okay.
Okay, and now I need to change the lemma, so I need to again explain why it implies 1 here. But my explanation doesn't change much. We will, so here in the lemma U is fixed, but we can as well take a random U. And then picking a random half to be S is the same as first picking S randomly according to P and then picking T randomly to P. So nothing changes, just one more step to get 1 from it. Okay, and now it becomes easy to prove it. Okay, so U is already fixed. And now let us fix G and H that makes at least K mistakes. And so if G doesn't make K mistakes on U, it doesn't contribute to this probability. So here we're using that the learner is consistent. So it will pick a function from H, and we will say that there are no such functions G with probability at most 2 to the power K. So we fix G. And then if we pick a random half probability that WG, the set where G makes a mistake, belongs completely to the training set. Is at most 2 to the minus K. And this is because of seminar exercise. Remember, there was a bag with even number of elements, of which some number K are marked. Take half of the bag, probability that non-marked elements are taken is at most 2 to the minus K. It's precisely the same thing here.
This goes when we pick unmarked elements, the probability that we will pick a mark in only exists.
Yeah. So with this conditional probability.
I have a question about definition because I skipped the first.
Yeah.
It's about growth function.
Yeah.
So when the set size is equal to wait a minute. But when it's equal to what should be n, so that growth function of n is equal to size of h.
Growth function is equal to size of h.
When it's true.
Then n needs to be the size of x.
Okay, so
And
I
then
just
it's the size of h. Yeah, you're right. Good point. Well, and if x is infinite, yeah, then okay, we need to have growth function of infinity. But okay,
I just asked it to be sure that I
yeah,
understand.
yeah, it's a nice question. Okay, so yes, let me. I was explaining this. So probability that mistake set of G intersects S. That does not intersect S is at most 2 to the minus K. And this is for a fixed G and H. And now we want to apply union bound. So it looks like we're again in our bad situation because H can contain infinitely many elements. And so the union, we need to do it for each G and H. And so it looks like no progress here, but it's not true. Because now we fixed U. U is a set of 2n, of size 2n. So we only care about the values of our functions inside U. Values of functions outside U do not matter to prove this claim, because again, U is fixed. So we just need to count the different functions inside U. And this is precisely what growth function is doing. So when we apply union bound, so here the problem is fixed. For fixed G, we have to look at this event. But in order for proper consistent learner to be good, we need that for all G with this property. We need to avoid all WGs for G with this property. So we apply the union bound, but not over all functions in H, but over all functions that are non-equivalent in U.
So we multiply this by growth.
By growth function.
Okay.
Yeah, so this bound K is multiplied by growth function, and that's why we get here this value. 2n is the size of U.
Mm-hmm.
And so this lemma is proven. And that means two lemmas together, we have proven one. And so proof is finished.
Could you please explain once again how we get growth function in the last proof?
Yeah. Okay. So in lemma, we have fixed u of size 2n. And we only care about intersection of mistake sets inside u. So we can think that x is equal to u. Right?
Mm-hmm.
So we can pick like one function. We don't care about values of functions outside u because they cannot change the size of this set.
Yes.
Okay, so when I say fix g and h with this property, then we conclude that training set avoids every mistakes of g with this probability. And now we want that this to happen for all possible behaviors inside u. So we want to apply union bound, but not on all functions in h, but all equivalents, but all functions when we restrict h to u.
Mm-hmm.
And so, but this is how many functions are there, and this is precisely the definition of growth function. It is how many functions we have if we restrict the input to u. So here will be the set x1 till 2n. So there is the factor 2n here.
Mm-hmm. Okay, I see. Thank you.
And so one is proven. Okay. And now I will finally tell what is VC dimension. So, oh, maybe I will keep it a little bit and delete the proof. Yeah. Okay.
I think you should keep the left side and
Yeah, that's what I say, but then I need to delete the right side. Okay. So VC dimension is the first value of growth function that is strictly smaller than 2 to the power n. Okay, that's complicated definition, but that and directly implies that either growth function equals 2 to the power n or is bounded by some polynomial. So it's kind of amazingly strong property that's at the core of why learning is possible with such worst case guarantee. Okay, so definition is a set is shattered if we can see all dichotomies. So a set U is shattered if all possible vectors of length n, all 2 to the power n possible vectors can appear using some function of h. So set S is shattered if size of, okay, I should say list S is shattered 1 till xn shattered if or I can write it even better like this. H is equal to y to the power s. Okay, it's near the border. I hope you can see. I didn't pin my video. Okay. So here, if this set is equal to y to the set of all functions from s to y. So that means that the size is equal to 2 to the power size of s. Like this. Or, yeah. Or equivalently, if in G tilde S is G tilde of x1 till x10 is 2 to the power n. And the VC dimension is the largest size of a shattered set. Each shattered set. So let us do an example for interval classifiers. So indicators on intervals. So I claim that VC dimension is equal to 2. Or let us have threshold functions. VC dimension is equal to 1. And so VCT is equal to 1. Why is it? 1 point can be shattered. What does mean 1 point to be shattered? Well, if we consider all lists of length 1, it means we can get the label -1 and +1 just by moving the threshold right or left. So we choose F. And so if we have points 0 and 1, but we cannot get all dichotomies. By the way, such a list of labels is called dichotomy. So for the input x, let's use 2 and 3, do not confuse them with labels. So we cannot get all dichotomies. We can get -1, -1. Can get -1, +1, we can get +1 and +1, but we cannot get +1 and
This is
-1.
because those first are method.
Yeah. So threshold classifiers. Interval classifier. So what's VC dimension for interval classifiers? So indicator on interval.
So there are some classifiers look like -1s, +1s, and -1s later. Okay.
Yeah. Something like this. So -1, +1, -1. So what is VC dimension? So can we shatter a set of size 2?
Yes.
Yeah. So we can have all 4 dichotomies for a set of size
But
2.
we can have +1, -1, and then +1.
Yeah, exactly. So that means VC dimension. So it is at least 2. But then for every set of 3 points, so when we have 3 points, we can order them. And then we can say that, +1, -1, and +1 is dichotomy we cannot produce. So note that it's like every year there is a mistake. People make mistakes in definition. So to prove that VC dimension is at least some k, value k, we need to find k points that are shattered. And to prove that it's at most k, we need to find k + 1 points that cannot be shattered. And so students flip this. They say, oh, I found k + 1 special points that cannot be shattered. Therefore, VC dimension is at most k. So yeah, be careful. So for upper bound is the hardest job. You need to make a proof for all k + 1 points. You need to tell dichotomy doesn't exist. Okay. So let's do some examples. And I need to make space, so I will remove it. So next one is rectangles. X is aligned rectangles in the plane. So what is VC dimension? Well, rectangle. So we will use rectangles in the plane, but they have to be axis aligned. So horizontal here, vertical here. So my claim is that 4 points can be shattered. So we have +1 inside and -1 outside. So VC diamond, can we shatter 4 points? Can you find 4 points that are shattered? And okay, I just to speed up a little bit. Here are 4 points, and they can be shattered. Like all plus we put over, we can put like this when there are two. Any choice of 2 points we can shatter, but 5 points cannot be shattered. And why is this? Well, when there are 5 points, let us choose a point, the rightmost point, and let us make it plus. Let us choose the leftmost point. Let us make it plus, the topmost point plus, and the bottommost point also plus. We've chosen 4 points. The 5th point will be minus, but this 5th point must be inside. So for every 5, and so we cannot realize it. This point must be also plus, because in the inside of the box we just constructed. So 5 points, and this is also in d dimensions. So X is a line boxes in d dimensions have VC dimensions 2D, because for every dimension we go from bottom, top, and so on. Now, next one, homogeneous half planes, half spaces in plane. And so now, no, so let us just say non-homogeneous, just half spaces. So input is all of plane.
What's homogeneous?
Yeah, I will say later. So now let us have plane, and let us consider halves of the plane. One half is plus, the other half is half planes. Okay, so what is VC dimension? So what do you think?
I think it is 2 or 3.
Yeah, so 3 points is easy to shatter.
You can draw a
Always,
line.
yeah. Or here. Okay, 4 points. Can we shatter 4 points?
I guess not.
No, because let's consider 2 cases. Either 1 point is in convex hull of the other ones. Then what dichotomy can we?
Plus on
the outside
and
yeah.
inside minus.
Minus, and so we cannot make it because a point inside convex hull is always in the same half plane. So it means half plane is here somewhere. But then when we go from one plus to another plus, we always stay on the same side of the half plane. Okay, and then the other case is that they're not inside half. So 4 points, and none of them is in the convex hull of the other ones. So what will we do then? Then the plan is, let's look to diagonal. And so 2 points on diagonal will be plus, and for the other diagonal, we will use minuses. And so now we have a problem, because when we go from one plus to another plus, we stay in plus. And when we go from minus to another minus, we stay at minus. And it's always possible to choose 2 diagonals that cross each other. Okay, this is some little argument. I will skip it because I will give a more general argument for any number of dimensions. So now let's go to homogeneous half spaces. So in d dimensions. So now X is equal to RD, and H is equal to all functions of the form sine of W dot product X, and W is also in RD. So these are homogeneous half spaces because the border goes through the origin. Like 0 is border point.
So homogeneous means that those half spaces are not shifted.
Yeah, and I claim that VC dimension of H, let's call it HD, is equal to D. So let's find D points that can be shattered. Yeah, so I try to hurry a little bit because I need to stop in 20 minutes.
Okay.
Yeah, It's right, 20 minutes, yeah. So coordinate standard basis. It's D points, and we can shatter them like we want. And so standard basis, so any dichotomy can be chosen by adding up. So W is sum of EI, for which YI is equal to 1. And it works. So if we take another, AJ is not, if AJ is equal to -1, then dot product will be 0. Okay, so now let us prove that D plus 1 point we cannot shatter. So let us say we have XD plus 1. So if there are D plus 1 points, it means that one point must be linear combination of other points. So we consider any D plus 1 points, but then let us say that the last one is linear combination of the first one. If it's not true, then rearrange the order. So we have alpha 1 x1 plus alpha D xd.
So its label is determined by labels of the other points.
Yeah, I will just, for convenience, say that the last point of our list is linear combination of the other, and otherwise you just choose the.
And its label is also element.
Okay, now which dichotomy we cannot make? Well, we will say I1 equals sine of alpha 1. Yd equals sine of alpha D. Okay, so then let us say that we have some W that predicts correctly the points 1 till D. Then I claim we have no choice for the label of D plus 1. So W will have the same label. So the label of the sign of okay, so let us look to the sign of W times XD plus 1. Well, XD plus 1 is equal to this thing. So it is the sign of alpha 1 x1 times W plus alpha n alpha D xd times W. Okay, if W has all these labels right, that means that all of these things, they are at least 0. And so that means that this must be at least 0. So the dichotomy we cannot produce is a dichotomy where D plus 1, so Y D plus 1 equals -1. And then these Y's. So we can't make, and so VC dimension is at most. So again, this works for any set of D plus 1 point. Okay. That's enough. So normally VC dimension, so if H is a set that can be parameterized by K parameters, then VC dimension is usually equal to K. But there are exceptions. Sometimes it's a little bit more. And there is one extreme exception, like for sinus functions. So the class of functions. So the sine of 2 pi a x. And here a is natural number. So this is a set of classifiers defined by sinus functions. It has infinite VC dimension, but it has only one parameter in its definition. Oh, yeah, and I forgot, like inhomogeneous half planes. VC dimension of inhomogeneous half spaces is D plus 1.
Yes, because for 2 you give an example when we can shatter 3 points.
Yeah. And this is more general, and we prove it just by looking at homogeneous ones and fixing the last coordinate. So and then follow the proof. So yes, the spheristic that's equal to number of parameters is quite good, but not perfect. Okay. Yes, and now the last task, we need to prove this inequality. And also, I didn't have time to look to it. Well, I will. In the notes there is about balls in RD. You need to read by yourself. And now we will have this amazing bound. Actually, there exists another bound, also quite impressive. H of n is bounded by n to the power VC of h. So that's easier bound. Sorry, n plus 1. We need a little more.
May I ask a question, please?
Yes.
So the VC dimension of half spaces is 3, and for like D at most 3, we have VC dimension D.
For D at most.
For linear classifiers.
Yeah, it's true for what I said. It's true for all D dimensions D. 1, 2, 3. Maybe not for 0. That's a strange case. Yeah.
But didn't we prove that VC dimension of like for D equal to 2 is 3?
3, yeah, and that was for inhomogeneous half spaces.
Oh, okay, I see.
Yeah. So inhomogeneous, it's 1 more. So I will first give the proof of this inequality. And I need to look to it because I forgot a little bit to my paper. Yeah, so proof is by induction on n. So we will assume that we have proven it for fixed value of n and all classes H. So this is induction. So well, first, if n is equal to 1, then this thing is obviously true, right? So if n is equal to 1, then growth function.
What is the bound on growth function when n is equal to 1? It is 2.
Yeah, it can be at most 2 because in 1 point we have at most.
And
so 1 plus 1 to the power VC dimension. So for
VC dimension is positive.
Yeah, okay. Well, VC dimension can be 0, but if VC dimension is 0, so VC of H is equal to 0. If
this can be 1, 2 if VC dimension is 0.
Yeah, so if VC dimension is 0, what does it mean? It means that H cannot shatter 1 point. And so it means that H is equal to 1. Or H contains 1 function. And in this case, we are also good. Oh. Now, plan is to do by induction of n. So, so I am looking at the note. So let us look at G tilde of a set x1 till or a list n minus 1. And by induction hypothesis, we know it is at most n to the power Vc of h. Right? Okay. Now let us look at point xn. And let us look at point xn and some f and h. And we say that f has a mirror and h if there exists a function g that has the same values on x1 till xn, but opposite value on xn. And so exists g and h such that fx1 equals gx1 till fxn minus 1 equals g minus 1 and fn not equal to gx. Okay, now next step we need let us now look to all dichotomies. So imagine that we have n is equal to 3, so we have 2 points. There are a bunch of dichotomies 1, 0, 1, 1. So let us consider 4, and we add now let's now look to x3, and it can happen that x3 has 2 dichotomies here, maybe another dichotomy here, but here the values are fixed. So we have a 1 here and a 1 here. Let's use the same one. So what we see is that when we consider x3, we have, of course, more dichotomies by monotonicity, and but not all dichotomies might split into 2. And so let us consider 2 classes. Let us consider a special class H prime. And H prime contains all F and H that have a mirror. So F has a mirror. Okay. So now we can write some inequality for so all dichotomies after adding x3. How many dichotomies do we have after we add x3? We have all the dichotomies we had before on the 2 points.
H prime.
Yeah, plus number of dichotomies of H prime, but only on x1 and x2. So now we reduce the problem from looking to 3 elements to 2 elements by looking to the special set. And we can apply induction hypothesis. So let me write it. And so G of x1 till xn, it is equal to dichotomies on H for x1 till xn minus 1 plus number of dichotomies for the special class H prime. G H prime of x1 till xn minus 1.
So what if we have H prime size equal to H size?
That means all functions have mirrors.
Yes, and
It can happen, yes.
Can we apply induction here?
Yeah.
Okay, I see.
Yeah, and so now we are like almost done. because now this H prime, what do we know about VC dimension of H prime?
It's less or equal to.
No, it is at least n.
Yeah, so okay, I'm cheating a little bit. Let's throw away this new point xn from the input. So okay, f has mirror, and let us restrict f to the points without xn. Okay, so then let's compare the VC dimension of H and H prime. We know that if we add or maybe okay, sorry, let's fh has mirror, and let's fix the label, it's better, sorry. fxn equals to -1, for example, if labels are -1 and +1. Okay, so now it's still true, or sorry, I was using 0 in the example. Okay, so now it's still true, right? So number of dichotomies by this function equals, well, actually before it was not true, because here we have twice the number of dichotomies. We've counted them 3 times in total, so I had to restrict this thing. Yeah, sorry. Okay, so now number of dichotomies is equal to number of dichotomies of original class plus the number of dichotomies on the new class. But by fixing this label to 0, we know that all these functions have their mirror label. By fixing this label, the VC dimension must drop by 1, because any set that's shattered here, after we add their mirrors, we have another element. We have the other dichotomy. So we know that VC dimension of H prime must be strictly less than VC dimension of H. And now let us look what happens to our bound. So we know this thing. And we know for H prime we have the same, but with VC dimension 1 smaller. Okay, I need to delete the finish. So what we have here is that G tilde of x1 till xn is bounded by n to the power VC of H plus n to the power n to the power VC of H minus 1. Okay, and so this is bounded by n plus 1 to the power VC of H. And so we are finished with induction step. So we started from here and something similar for H prime. And we proved this.
You look at the piece.
Yes, good point. Okay, so then to get this bound, it's completely the same philosophy, except you have to be a bit more careful, like do this calculation a bit more precise. You can do it directly, and in the notes I made like some more general, even more general thing.
We don't need any ideas about the previous part of the proof. We just need to be careful.
Yeah, just repeat all this, but be careful with this plus, because I was not careful here with this upper, like it's not tight, right?
Okay.
Yeah. Okay, so now I will put on Telegram the quiz. On Telegram. Oops, sorry for I don't, yeah, I didn't see the message. Okay, so here is the quiz, and then I will stop the streaming.